ওরকম হয়, ঠিক আছে। অনেকবার আমরা হয়েছে।
Any questions? Okay, so we'll begin. So today we basically want to study cosmology, which is the study of the universe as a whole. Okay. But before we do that, we have to introduce some notion of isometry. Okay, this is something that we had discussed once in the context of Schwarzschild black hole, but let me try to discuss it in a more formal way. So isometries are special class of general coordinate transformations. Special type So let's recall that under a general coordinate transformation, we have this equation So a particular general coordinate transformation will be called an isometry. Called an isometry if G prime mu nu of x prime is G mu nu of x prime. So in other words, if the transform metric G prime mu nu has the same functional form as the original metric, then we call this transformation an isometry. Okay, so notice that this on this side we have x prime in the argument, so that basically means that as a function these two are equal, G prime and G. Now not all metrics have isometries. Okay, there may be metrics which have no isometry at all. Okay, there may not be any coordinate transformation which satisfies an equation like this. Okay. But we can of course also consider metrics with isometry. So let me give the example. Flat Minkowski spacetime eta mu nu, so G mu nu equal to eta mu nu. This has Lorentz transformation and translation as isometries. So if we take x mu, or x rho, okay, take a general transformation of this kind, where you translate x by a, and at the same time you can also make a Lorentz transformation. This is a Lorentz transformation matrix. This is of course rigid. Okay, no x dependence here. Then the new metric in the prime coordinate system will also be eta mu. Okay, this is the reason why we call Lorentz transformation a symmetry of flat space. Is this point clear? Okay, so exercise. Check that G prime mu nu of x prime is also eta mu. Okay, then if you start with G mu nu equal to eta mu nu and then make this transformation, in other words, you substitute eta mu nu on this side or eta rho sigma on this side, and then here, you, for example, you will get a lambda rho mu, this will give you lambda sigma nu, and then by the properties of a Lorentz transformation matrix, it will give you back eta mu.
So we use lambda, eta lambda transpose.
Yes, so you have to use that lambda eta lambda transpose equal to eta. That's what you mean by Lorentz transformation.
So that's then this itself shows that
Yeah. So basically this side will become lambda eta lambda transpose. Okay, the mu nu component. Okay, that's the way you correlate that.
I'm saying that the definition itself of lambda, that was
Yes.
that itself shows that it doesn't change.
Yeah. So in essence, you consider that you can start with a general matrix of this kind and ask under what condition is this an isometric, and you will find that you need this condition. Lambda eta lambda transpose. Similarly, if you take 3 Euclidean dimensions, Gij equal to delta Ij. Here, just rotation is an isometric. Rotation plus translation. So xi equal to Rij x prime j plus Aj, where R, that is called RR transpose.
So in that equation, the old coordinate x is expressed in terms of the new one. The x rho is equals to lambda rho mu.
Yes, so this is the relationship between x and x prime. You can also invert this. Write x prime in terms of x. Okay, I have written it this way because it's easiest to substitute here. But you can always invert this and write x prime as lambda inverse times x plus another translation. But this is a coordinate transformation I have taken. Okay, the idea is that if you take this coordinate transformation, substitute here, calculate these objects, then the right hand side becomes equal to eta mu. That's what you started with.
Then x prime mu, right?
X prime mu. X prime mu. Is this clear? Okay. So isometry essentially is this statement.
So what is the physical meaning?
Physical meaning is just like symmetries of the metric of the background. Right? That the eta mu nu background where a metric is equal to eta mu nu is unchanged under these transformations. So if under these transformations x goes to x prime, then x and x prime will physically look the same. Right? Because there is a coordinate transformation in which you can make the metric around x prime look the same as the metric around x. So
Function form remains the same.
functional form of G remains the same, exactly.
That is isometric.
That is isometry. Okay. But so the point is in general, okay, suppose you make a transformation, it takes x to x prime. Okay. Then G prime and G being same, okay, means that it's as if the metric around x prime has become G mu. Right? The metric at x prime has become G mu. But x prime is physically different from the point x. Okay. So if there is an isometry, that means that the point x and x prime, right, are physically equivalent. Okay. Because even though the original metric G mu nu, okay, didn't have the same value at x and x prime, did not have the same value. Okay. But by making this coordinate transformation, you make the metric around x prime look what it was around x earlier. Is this, so let's take translation. X, forget about, suppose we take x rho equal to x prime rho plus a rho. Right? What does it mean physically? It physically means, suppose you start with x prime, right, and make a translation, then the metric around x prime and metric around x prime plus a, they will look the same by appropriate coordinate transformation. Is this point clear? Are there any other questions? Okay. Now, suppose we have a metric with certain isometry. And now we write the metric in a different coordinate system. Okay? So the metric will look different. The functional form of the metric will change. Okay. Will this have the isometry? And
Should have.
yeah, the point is that it should have the isometry, because if isometry is a physical attribute, right, then it shouldn't depend on what coordinate system you have chosen.
But sir, is it true for any types of coordinate transformation or a particular group of coordinates?
No, any general coordinate transformation. Take a metric with certain isometry and you make an arbitrary general coordinate transformation.
Okay.
Okay. The question is, if the original metric has an isometry, will the new metric have an isometry? Okay. So if the new metric, if you have to prove that the new metric has the isometry, okay, what you have to do is to find an appropriate transformation that preserves the form of the new metric. Okay. And the way you can find this transformation is if you take the new metric, okay, take the inverse of the coordinate transformation to make it into the original metric. Okay. Then you make the isometric transformation, okay, which you know preserves the form of the original metric. Okay. And then you make the same coordinate transformation that you had made earlier to go to the new metric.
So the functional form of the original is same final form.
Yeah. So the point is, if the functional form are the same. So the point, let's say suppose you have two metrics, G and G prime, which are whose functional forms are the same, and isometry relates these. Okay. Now you make some arbitrary coordinate transformation to go to G tilde. Okay. How will you see that G tilde has an isometry? Okay, that's a question. And the answer is that you first make the inverse of this coordinate transformation, make it into G. Then you make the isometric transformation to go to G prime, which is the same as G, because G prime by definition has the same functional form as G. Okay. And then you make this arbitrary coordinate transformation again. If G and G prime have the same functional form, then it's clear that G tilde and G tilde prime would have the same functional form. The same coordinate transformation makes it G tilde. Okay, because G prime is equal to G. Is this clear? Okay. So then, this combined transformation is an isometry of G tilde. Right? Because you started with G tilde and you found a coordinate transformation which is non-trivial, okay, which is not identity, because this of course would have cancelled this, okay, if you didn't have this. Then it will be a trivial statement that identity transformation doesn't change G tilde. But what you are doing is that you are making an inverse transformation, then making this non-trivial transformation which is this isometry, and then going back. Okay. So this process generates an isometry of G tilde, but the actual form of the coordinate transformation of course will be different. Is this statement clear?
This is going from G tilde to G tilde only, because finally that G tilde is in the same coordinate system. Like upper G tilde is also in terms of some coordinates.
Yes.
Lower G tilde is also in the same coordinates, right?
No, it's not the same coordinate system, because in the middle you have made this isometric transformation. So this whole transformation is a non-trivial coordinate transformation. Right? If you didn't have this, right? If you went to G tilde to G and then came back again from G to G tilde, then it will be the same coordinate system, because you are just cancelling it, right? You are just making inverse transformation to go from here to here. Okay? But what you are doing is that you are making this inverse transformation to go to G, okay? Then making a non-trivial coordinate transformation, is the isometric transformation, okay? And then making that coordinate transformation to come back to G tilde. Okay? So you are composing, if you think of it as a composition, that you first you make F inverse, then you make the isometry, F isometry, and then you make F. Okay. So first you go from X to F inverse of X. Okay. Then from F inverse of X you go to F isometry of F inverse of X. Okay. And then you go to F of that. Okay, this is the combined coordinate transformation that you are making. And the idea is that if this, so this will change G tilde to G. Okay. This one will preserve the form of G. So it will take G to G. Okay. And because F takes G to G tilde by definition, okay, and because the isometry hasn't changed the form of the metric, the next step will bring it back to G tilde.
help with one thing. Could you assign the coordinate labels to each?
Yes. So let's suppose the isometric transformation is x equal to f of x prime. Okay. So this preserve the form of the metric. Now suppose that we want to go to an arbitrary coordinate system y mu, which is some g mu of x. Okay. And the inverse of this is x equal to g inverse. Well, maybe g is not the right word. H. The inverse of this is h inverse mu of y. Okay. H inverse by definition is the inverse function. Okay. So if you want to see the isometry in the y coordinate system, okay, what you need to do is that you first have to go to the h coordinate system. Okay. So you first go to h inverse mu of y. Okay. In this coordinate system, the metric takes the form of the original metric g that was there in the x coordinate system, where you know how the isometry acts. Okay. Then we apply that isometry, which is f of this. Okay. And then you apply back h of this. Okay. Let me just remove the mu coordinate, mu level. Okay. Just abstractly y equal to h of x. So this is the combined coordinate transformation. That will have an isometry of the metric in the y coordinate system. Right? Because you are first going to from y to x coordinate system, where the metric had the original form, in which you know how the isometry acts. Then you add to the isometry, and then you go back to the original coordinate system. So let me give an example. Okay, because this can sometimes make the isometric transformations look non-trivial. Okay, from a
Just one question. If I have the coordinate system y,
yes,
if we just act f on y,
yes,
then I will get some another.
it will not be an isometry in general. No, it will not be an isometry. Okay, so I will give a simple example. I think it should be familiar to all of you, but it's just that in this abstract notion it looks a little complicated.
After rotation, if we give a translation, that will not be clear.
Yeah, it's not even rotation to translation. So let me. That's another. That will be another example. But let's suppose we have x, y, z coordinate. Okay. And the isometry, we know there is a rotational isometry. Okay, let's forget about the translation, which takes this to r times x prime y prime z. Okay, that's normal Euclidean space. Okay, metric is dx square plus dy square plus dz square. Okay, and clearly under this transformation it becomes dx prime square plus dy prime square plus dz prime square under this transformation. But now we want to change coordinate, and let's suppose we want to go to the spherical polar coordinates. So this I can write as dr square plus r square e to the square plus sine square theta d phi square. Okay, new coordinate system r theta phi. Now the question is, how does isometry act on the r theta phi coordinate system? How does this rotation act on the r theta phi coordinate system? It's in general a complicated transformation. You know that r doesn't change, but how it acts on theta and phi is not trivial. Okay, rotation about z axis is trivial in terms of theta and phi, right? It just translates phi. But rotation about x axis or y axis, or a general rotation, acts non-trivially on theta and phi. Okay, so how will you find those transformations? Okay, suppose you have some rotation matrix which is given to you. And you want to know how to find how does it act on theta and phi. So what you have to do is that you have to start from a theta phi coordinate system, okay, and then work out what x, y, z are. This, for example, is r sine theta cos phi. This is r sine theta sine phi, and this is r cos theta, right? And you can invert this also. So what you have to do is you have to see how it acts on the xyz coordinate system, right? So you go back from theta phi, r theta phi to xyz. Okay? You see how it acts on the xyz coordinate system. Take this new transformed xyz and then re-express that. So x prime y prime z prime, which is related by this, you now write as r prime sin theta prime cos theta prime, r prime sin theta prime sin cos phi prime sin phi prime, and r prime cos theta prime. Okay. So you know the relationship between x prime, y prime, z prime and x, y, z. Okay. And this implicitly can give you the relation between the r theta phi and r prime theta prime phi prime. Okay, this is the way you will figure out how the isometry acts on the theta phi coordinate system. Okay. You can easily check that r is invariant, but action on theta and phi is highly non-trivial. Okay, but this is the rule that if you know the isometry, form of the isometry in some coordinate system, you can always find what it looks in the another coordinate system, because you can first go back to the original coordinate system in which you know how the isometry acts, okay, make that isometry transformation and then go back to theta phi coordinate system.
Just because f and h do not commute in general.
Exactly. So in general f and h do not commute, so this is not going to be the same as f. Okay. But the form of the isometry clearly will change, right? It's not that r theta phi will be replaced by the same matrix times r theta phi under isometry. Is this point clear? So, as I said, not every metric has to have isometry, okay, but many of the metrics that we deal with do have isometry. For example, take Schwarzschild black hole metric, Schwarzschild metric, right? What kind of isometries will it have? It has rotational isometry, right? It's not visible, it's not because you don't have the xyz coordinates, you have the r theta phi coordinate system, but since you know that this combination is invariant under the isometry, okay, which is not trivial but which you know has to be true because it was there originally in this coordinate system. Okay, we know the Schwarzschild black hole will also be invariant under the same isometry on theta and phi, same transformation, right? Because this part is the same. The theta phi dependent part of the Schwarzschild metric is exactly this.
Sir,
Yes.
any of the symmetry of the metric will be an any under.
Yes. So isometry basically is the symmetry of the metric, right?
So there are also time translation symmetry.
Yes. So there is also time translation symmetry. Right? That's also another isometry of the Schwarzschild black hole. So these are the isometries of the Schwarzschild black hole solution: time translation and rotation.
Spatial.
Spatial rotation, arbitrary spatial rotation. Are there any questions?
So here x, y, and x prime, y prime, z prime
Yes.
are two different physical points of a manifold.
That's right, yes. In general, there are different physical points, x, y, z and x prime, y prime, z prime. Okay. That's why isometry says that if two different points are related by an isometry, then effectively those 2 points are equivalent, right? The metric looks the same in around those points, even though when you have written the metric, it may not look the same, right? That there is some coordinate transformation, you make the metric look the same. Okay. Here, for example, the point theta equal to 0 is very different from the point theta equal to pi by 2. Right? But nevertheless, because we know there is an underlying isometry that can take the point 0 to the point theta equal to pi by 2, we know that those 2 points are equivalent, right? Even though it's not manifest from the form of the metric that is written here. Okay? Because it's a non-trivial coordinate transformation that is needed to make them do. Okay. So another useful notion is the notion of infinitesimal isometry. So these are essentially infinitesimal general coordinate transformations which are isometries. So these will take the form x mu equal to x prime mu plus epsilon okay, where epsilon is a infinitesimal parameter. And then one might ask, what condition does xi mu has to satisfy in order that this is isometric? So g prime mu nu, we can calculate this. G prime mu nu of x prime is given by del prime mu x rho del prime mu x sigma g rho sigma of x. Okay, this is the definition of, this is the general coordinate transformation. Now let's calculate this. So del prime mu of x rho will be, so x rho is x prime rho plus this, so this is delta mu rho plus epsilon del prime mu of xi rho x prime. Then delta mu sigma plus epsilon del prime mu of psi sigma of x prime, and then g rho sigma of x plus epsilon xi, x prime plus epsilon xi. Okay. And now, because we are looking at small epsilon, this part we can expand in Taylor series expansion and keep only the first term in epsilon. So we get this as g rho sigma of x prime plus epsilon psi tau
Sir,
yes.
G rho sigma, the argument is x.
Oh, x prime. Sorry, x. Yeah. Yeah. And so, yeah. So x I am replacing by x prime plus epsilon xi of x prime.
Oh, sorry.
So here it was x. Okay.
So our definition of isometry was up to the first order here.
No. So infinitesimal isometry means you check up to first order only. Right? The general definition of isometry was not for infinitesimal, that was for a general transformation. But now we are checking that what is the condition for an infinitesimal transformation to be isometric. Right? If the transformation is infinitesimal, you can work to order by order in epsilon, right?
Yeah.
Okay, so you are working up to first order in epsilon. Okay, and then you will demand that g prime mu nu of x prime should be g mu nu of x prime. That's the condition for isometry. Okay, right now of course we are not imposed the condition. We are just expanding this out. We know the general coordinate transformation rules. Okay, and we are just using that to expand these things out.
What is tau?
Tau is just an index. Okay, this is because Taylor series is expanding around x prime, right? This is a vector, right? So Taylor series expansion will involve epsilon xi tau delta or del prime tau. Because everything is expanding. So you can now multiply out the product and keeping only terms of order epsilon. So leading term of course comes from choosing these and this. So leading term is g mu nu of x prime. Then we can pick this term from here and then the leading terms from these two. So that gives you g Okay, so G rho sigma delta nu sigma, right? So that makes this into G rho nu. G rho nu of x prime del prime mu of xi rho of x prime plus these are all epsilon. Epsilon. Now I pick the delta mu rho from here and del prime mu xi sigma from here. This essentially makes this into
G mu sigma.
G mu sigma. Plus epsilon. Now we pick both mu and nu, so that makes this into G mu nu. So epsilon xi tau x prime del tau mu sigma. G mu nu. Because rho and sigma have become mu nu because of delta function.
Delta prime.
So del prime.
Del prime. Is this clear? Now, because these are already of order epsilon, I can just replace x prime by x. Okay? Because the x prime and x differ by order epsilon. Okay? So because you already have terms of order epsilon and you are ignoring order epsilon square terms, it doesn't matter whether you write x prime or x.
Yes.
Okay, so
All of them are means x prime anyway, so if you replace x
yeah, so I can just, because x prime is the argument, it's a dummy argument, so I can always replace x prime by x. That's another way of saying this.
But we already have a G mu nu x prime.
Yeah, so this of course cancels this.
Yes.
Right. So okay, so this so far I have not said anything about isometry. Okay, but now we note that if we want this to be an isometry, then it must be G mu nu of x prime. Right? That was the statement of isometry. The G prime mu nu should be G mu nu, right? With the same argument. So G prime mu nu of x prime should be G mu nu of x prime. That's the statement of isometry. So these two cancel, and we get G rho nu del mu xi rho. I am not even writing the argument. Plus G mu sigma del mu of xi sigma plus xi tau del tau G mu nu equal to 0. Okay, all the order epsilon terms, they are order epsilon square terms, which you don't care about. Is this okay? And I'll leave it as an exercise to check that this can be written as d mu xi rho G rho nu plus G mu sigma d mu essentially what I have to show is that, so first of all, d mu contains a ordinary derivative, del x. That's already clear.
I can put this G rho nu inside.
Yeah, you can, but first, I mean, let me try to explain how this comes. So basically, d mu will act as a del x cube plus a gamma. Yeah, so there is a Christoffel symbol coming from here. There will be similarly Christoffel symbol coming from here. What you have to show is that the sum of those Christoffel symbols is precisely what you have here. This term basically produces the Christoffel symbols that we need for making the ordinary derivatives into covariant derivatives. And now, since G is covariantly conserved, right, covariantly constant, so d mu 0 sigma equal to 0, I can write this as d mu psi mu plus d mu psi mu 0, where psi mu is basically g mu rho psi rho. Okay, you can write it this way or you can write it this way. Okay, it's exactly the same equation. Okay, because you have just used the fact that covariant derivative of the metric is 0 with the crystal.
This in some sense is like derivative of the concept charge.
Well, it's this psi is not really conserved charge, right?
Psi is not, but means if this can be written form of a total derivative.
But see, it's not a total derivative. See, these are divergence. Okay, it's not in the form of the conservation law. Okay, because it's symmetrized derivative. Okay, conservation law takes the form of d mu j mu equal to 0, right? Mu in this context. It's not that. So these vectors which satisfy this equation are what are called killing vectors. So xi mu is called a killing vector. So for continuous isometries, okay, isometries which are labeled by a continuous parameter, which you can take to 0 to get infinitesimal transformations, we should have one killing vector for every isometry. Okay, for example, if you have rotational symmetry, you have that corresponds to 3 killing vectors, because you can have independent rotations about the x, y and z axis. A Schwarzschild black hole has 3 killing vectors corresponding to rotations about the x, y and z axis, and it has a time transition, so that's a 4th killing vector. Standard Minkowski space has Lorentz transformation, that gives you 6 killing vectors, 6 parameter group of Lorentz transformation,
4 translation.
and it has 4 translation. Okay, so there should be altogether 10 killing vectors for Minkowski space.
Each component is
No, a vector field, a xi mu that satisfies this is called a killing vector. So for a given isometry, right, you have the whole vector field. Right? It doesn't make sense to talk about a xi1 by itself. Right? The xi mu together, the xi1, xi0, xi1, xi2, xi3.
Oh, so when you are saying 3 kilometer means 3
Independent solutions to this equation.
Oh, okay.
Okay, that's what I mean by 3 killing vectors.
Now, what is the statement? The first statement that
Meaning xi0 by itself is not killing vector, right? It's the whole vector field. Xi0, xi1, xi2, xi3. Okay? That is what is called a killing vector. Okay? And the point is, for every isometry, continuous isometry, you should get a killing vector. That means you should get an independent solution to this equation.
So then, like for flat space time, your covariant derivative is just ordinary del mu, right?
Yes, that's
For
right.
that equation, you will have 10 solutions coming out from this equation.
Yes. The 10 solutions, I mean, basically easy to write down. One is xi mu equal to a mu. These are the
Constant translations.
constant, sorry. Xi mu equal to, so first killing vector xi1, okay, let me label it by this, is 1 0 0 0. This is the killing vector, right? Constant vectors are killing vectors because they, as I said, d mu is like the ordinary derivative, right? So any constant vector is a killing vector. This is time translation. Okay, xi2 is 0 1 0 0. Okay, this is 1, xi3 is 0 0 1 0, and xi4 is 0 0 0. So these are 4 killing vectors. The other killing vectors are linear in x. Okay. So xi mu has lambda mu nu x nu. For any, this is generator of Lorentz transform, not lambda mu. Let me write it as L mu nu. Okay, we had last time introduced the generators of Lorentz transformation, right? the infinitesimal Lorentz transformation. Okay, lambda is identity plus L. So these you can show satisfy also this equation. Okay. Basically, if you write in the lower component, xi mu equal to a mu nu x nu for a antisymmetric. This is clearly a Killing vector, right? Because del mu xi nu will be a mu nu, right? And this is symmetrized arithmetic. A mu nu plus a nu. Right? If A is antisymmetric, then this is 0. And there are 6 independent 4x4 antisymmetric matrices. Right? Those 4 independent A's will give the, those 6 independent A's will give the 6 other Killing vectors. These are the Killing vectors as well as Lorentz transforms.
So there is 4 gamma 0, a xi 0, xi 1, xi 2.
Yeah, so those are not independent vectors. For you fix an A, right? That gives you a set of vectors. Okay, so for example, suppose you take A as 0, 1, minus 1, 0, everything else 0. Okay, then that corresponds to xi 0, xi 1, xi 2, xi 3. So A, so if mu is 0, this vector as a function of x is a Killing vector. That's what it means, right? You have to choose independent A's, right? You cannot say that xi 0 is a Killing vector and xi 1 is a Killing vector. It doesn't make sense, right? The whole vector itself, right? A vector is defined by all its components. Okay? So when I say there are 6 independent Killing vectors, that means there are 6 independent vectors you can write down, each of which has 4 components, okay, which satisfy that equation. Is this clear that for any antisymmetric A, this will satisfy that equation?
Yes.
In flat space, right? And I am saying take a particular antisymmetric A, which is this. The corresponding xi calculated from here is this. Okay, because xi 0 will be 0, 1, this multiplying x0, x1, x2, x3, right? That's the matrix rotation. So 0, 1 times x0, x1, x2, x3 will give you, so A on x0, x1, x2, x3 will basically give you x1 minus x0, 0, 0. This is the Killing vector. Is this clear? Now, the fact that this equation is a tensor equation, like both sides, if you think of the xi as a vector field, then both sides are tensors, right? 0 of course is a tensor and this side is a tensor, which basically means that this equation is invariant under coordinate transformation, right? Let's imagine that you go to a new coordinate system, okay, and transform xi mu as if it's a vector. If in the original coordinate system it satisfied this, then in the new coordinate system also it will satisfy this, right? Because after all, tensors transform by multiplying by some matrices, right? And 0 remains 0 multiplied by any such matrix. Okay. So if xi mu satisfies this equation, then xi prime mu, okay, in the new coordinate system will also satisfy this with the covariant derivative written in the new coordinate system. Okay. And this also makes it absolutely clear that the existence of the Killing vector is independent of what coordinate system you are using. Right? The functional form of the Killing vector of course will change. Right? But if a Killing vector exists in one coordinate system, it will exist in another coordinate system. Just transform it by coordinate transformation.
This is the statement we started with. Like if we find an isometry in one coordinate system, we should find
it any coordinate.
coordinate.
Yeah. So which basically means that the Minkowski space, right, when you write the metric as eta mu nu, we know has Lorentz invariance, right? And in fact Poincare invariance, Lorentz plus translation. Now make an arbitrary coordinate transformation. Okay. The Minkowski metric looks very complicated in general. Right? You will not recognize that as a Minkowski metric if you make an arbitrary coordinate transformation. Nevertheless, even in that coordinate system, okay, there are exactly 10 killing vectors. Okay? And those 10 killing vectors you can find by starting with the killing vectors that is constructed here and then making a coordinate transformation. Okay? In the process of coordinate transformation, because these transforms has vectors, it will become complicated X-dependent coefficient. Right? Because vectors transforms as I prime mu, then the new coordinate system will transform as del rho x prime mu times I rho. Right? So in general, if x prime mu is a complicated function of x, these vectors will look very complicated function of its argument. Okay? So the form of the killing vector will change, okay? But the existence of these vectors is guaranteed. Okay? It's guaranteed that this will be a killing vector in the original in the new coordinate system. Because
it is a covariant.
Because this equation is covariant. Is this okay?
So how many killing vectors you have for the short shell radius?
4. For Schwarzschild metric we have 4 killing vectors: time translation and spatial rotation.
So if the killing vector vanishes, then
Yes, a killing vector may vanish at some point in space. Right?
no, not killing vector. This relation is 0. Then this is the isometry.
Yes, exactly. So killing vector is okay. A killing vector is a vector field which satisfies this equation. Okay? So killing vector by definition satisfies this equation. So killing vector is in fact a vector field. Right? It gives a killing vector means it's a set of xi0, xi1, xi2, xi3 given as a function of x. Okay? Given such a vector field, you can calculate this, and if that vanishes, then you will call that vector field a killing vector field. Okay, and existence of such a vector field implies the existence of an isometry. Is this okay?
Vector field around the point at which we want to check.
No, vector field, see, killing the notion of isometry is not around a point, right? An isometry is a statement of a relationship between the transform metric and original metric at all points in space. Okay? We wrote the isometry as g mu nu of x prime being g prime mu nu of x prime, right? This has to hold at all x prime. Okay? So the isometry is not a statement of a equivalence around a point.
But at a point in the tangent space level, we checking the isometry.
No, not at the tangent space level. Isometry is this statement. Coordinate transformation that preserves the functional form of the metric. And that translates for continuous isometries to this statement. Okay, infinitesimal version of this relation at all space-time points is that this differential equation must hold at all points in space-time. Okay, so this is a functional differential equation. So this differential equation on this function is I mu of x. If this is satisfied, if I mu is a solution to this equation, then we will call that it's a killing vector field. Okay, are there any questions? Okay, so now we turn to cosmology. okay, which is essentially the study of the universe as a whole. In other words, earlier we have been thinking of isolated objects sitting in flat space-time. Like Schwarzschild black hole, that's just a massive object sitting in flat space-time. Okay, we don't care about something being very far away. We just pretend as if we have just flat space-time with nothing else except a spherical symmetric object, right? Whose metric we are calculating. In cosmology, the viewpoint is quite the opposite. Okay, we don't want to consider isolated objects. Okay, we want to consider all objects in the universe at one go. Okay, the full metric. So when I talk about the G mu of x in cosmology, is the metric that is valid everywhere in space-time. Okay, so it in principle takes into account the effect of all stars, planets, galaxies, etc., whatever is there in the universe. Now clearly, to do this exactly is a very complicated problem, right? Because the universe has lots of objects, right? You don't even know what kind of objects the whole universe has. Okay? So we have to make some approximation, okay, and you have to make some approximation which is useful, okay, for the purpose that you want to use it for. And the idea here is that the stars, planets, galaxies, etc., those create local fluctuations in the universe. Okay, we have some in the solar system, we have some planets in some isolated regions. Okay. But if you are interested in learning about the universe at a very, very large scale, okay, we can simply average out their effect. Okay. Instead of saying that there is a solar system here, okay, or that instead of saying that the galaxies have stars, okay, or even clusters of galaxies have different galaxies, okay, we just replace it by the average density of all objects in the universe. Right? That's our energy momentum density.
So there exists a length scale.
Yes. So when the originally cosmology was proposed, right? When this idea was proposed, then of course people didn't know whether this is a good approximation or not. That's why there's any length scale over which this averaging makes sense. Okay. But now we know from experiment, okay, that if we average over very, very large length scales, okay, which goes far beyond the galaxies, the scale of the galaxies and so on, okay, then at sufficiently large scale, the universe starts looking more and more homogeneous, okay, which basically means that if we average over very, very large length scales, then the fluctuations in the average density, okay, in different regions of the universe goes down. Okay, larger the distance you average over, the smaller becomes the fluctuation of the density. Okay. So in this sense, okay, one can say that we can approximate the universe as being homogeneous. Okay, and I'll try to make it more specific what I mean by homogeneous. Okay. Namely that it should look the same in different regions. The other property which is related, but we will see that it's not quite the same, okay, is isotropic. Okay, which is if you sit at one point in the universe and look in different directions, okay, the universe looks the same in all directions. Okay. Now it would seem that it's the same statement as homogeneity. Okay, if the universe looks the same everywhere, then isotropy should be included in that. But I will make this more specific, and we will see that isotropy and homogeneity are slightly different notions. Okay, they are not completely. They are not the same. Okay, there can be universes which are homogeneous but not isotropic. However, we also know, again from experiment, that the universe is not invariant under time translation. Okay, because the universe actually evolves as a function of time. Okay, so time translation symmetry is broken. Okay. Now this makes the former statements a little strange. Because we are saying the universe is homogeneous, right? That it looks the same in all different regions, but at the same time, to compare different regions, okay, we have to fix the notion of a time. Right? If the universe was also time translated invariance, right, then it talks about comparing different regions of the universe, okay, without talking about at what time we are comparing them. Okay. But now, when you are saying that its time translation is non-invariant, it changes as a function of time, Okay. Now a statement of homogeneity, okay, at best can make sense if you are comparing the different regions of the universe at the same time. Okay. But this of course is against the spirit of general relativity, right? General relativity doesn't have a preferred time. You can make a coordinate transformation which mixes time with space, right? So in one coordinate system, two different points, space-time points may be at the same time coordinate, but in another coordinate system, the same space-time points may be at different time coordinate. Right? In fact, it's also part of a feature of special relativity. Right? Two events are simultaneous in one frame, are not simultaneous in another frame. So when you are talking about universe being homogeneous without being time constant and invariant, okay, we already have in mind that there is some kind of preferred time in the universe. Okay. It makes sense to compare different regions of the universe at the same value of the preferred time, okay, and only in that sense the notion of homogeneity makes sense. Is this point clear? Then if there is no preferred time, right, then what is the meaning of the universe being homogeneous? We are talking about at what time we are comparing, right? If universe was time constant and invariant, right? If there is time like if there is a killing vector which corresponds to time transition symmetry, then it would make sense, right? Because then you choose your time coordinate according to that killing vector, which where constant time stances at the so time transition corresponds to transitioning that particular coordinate, and then you can compare the same value of the coordinate. Here, even in the absence of such a killing vector, such a notion of time, we have to make a postulate that there is some underlying notion of time in cosmology, and it's only at the same value of that time that the universe looks homogeneous in different parts and isotropic in different parts. Okay, so we will now proceed by assuming that there is such a preferred time. Okay. Now, of course, eventually cosmology will have to explain the origin of such a preferred time. Right? In general relativity, there is no preferred time. So, what fixes a cosmic time? Okay, it must be some kind of initial condition, which, if I have time at near the end of the course, I will try to discuss this. Okay. But for now, we have to proceed by assuming that there is some notion of time which is preferred. Okay. And when you are talking about homogeneity and isotropy, the universe is homogeneous and isotropic, okay, at a given value of the preferred time.
So what is that preferred time is not the time of us or anything?
Time of?
What we measure the time? It's not.
Well, you can, if you want to find a practical definition of the preferred time, okay, that means you have to try to look for a specific frame. Right? In special relativity, there is no inertial frame. The inertial frames, there is no unique inertial frame, right?
Yes.
You can move. Okay. Here, the preferred time can be understood as the time, okay, or the preferred choice of inertial frame, okay, in which you are talking about this time, okay, is the one in which the cosmic microwave background radiation is at rest. That's one way of defining the preferred time. Okay, so this is something again we will discuss as we go on. Okay, that the universe has a some radiation field. The universe is filled with some radiation, okay, and once we have radiation, okay, then of course a object moving relative to the radiation, okay, sees a different kind of background compared to the object that is sitting at rest with respect to the radiation. Right? If it's a thermal gas, for example, so thermal radiation in a black box, in a black body, okay, then a moving object sees different environment compared to a fixed object, because that preferred frame is provided by the frame in which the radiation has black body spectrum. Okay, so that frame is a preferred inertial frame, and in that, at the time that is measured in that frame, is what we will call the preferred cosmic time. Okay, but so far, of course, we have not talked about microwave background, which will come later. Okay, so you basically have to proceed by assuming that indeed there is a preferred cosmic time, and we will write everything in that preferred cosmic time, okay, without even knowing how it comes about in the first place.
So means any observation that we make experimentally,
Yes.
means that cannot relate to anything which deals with this time difference.
We deal with this?
Means if you are thinking of a preferred time,
Yes.
if some observation contains some formula or some calculation which contains time difference of this preferred time, say del t,
Yes.
so that cannot enter for any observed quantity that we.
Well, you can infer, right? So how the universe evolves as a function of time. Okay. See, once you make the assumption that the universe is homogeneous, okay, then you can study the time evolution of the universe by looking at radiation that is coming from far. Okay, because you know that the radiation that is coming from far, okay, the region from which the radiation is coming, if it differs from the region in which you are in, it's not because that's a different region in space, but because you are observing it early in time. Okay, so you ascribe all such differences to the time evolution of the universe rather than the spatial variation. Okay, so this way you can, find how things evolve in that spatial time. Okay, so we'll call T the preferred cosmic time. In which a given time slice looks homogeneous and isotropic over large scale. So we take the coordinates as t, x1, x2, x3, and these together we call denoted by the vector x. So what we will do is we'll start by writing down the most general metric that we could write down, and then we will see what is the how that metric is constrained by this notion of homogeneity and isotropy.
So here also the origin of the spatial coordinate has no any hurt.
Yes, the what is, we know that something is spatial about this time t.
Not about the spatial.
No, space coordinates can be arbitrary. Okay, so and we are going to exploit that. Okay, so space coordinates at this stage do not have any preferred coordinate system. Okay? Only the time is preferred. So any further coordinate transformation that you have to make to simplify things will involve the space coordinates, but we are not going to change time. Okay, well, if you change your time coordinate, then that means you are going from the preferred time to a non-preferred time.
And in that case, homogeneity will not.
In that case, homogeneity will not manifest. Okay? Again, as long as it is a statement of isometry, okay, any isometry in any coordinate system will imply isometry in a different coordinate system. Okay? But it will not look simple. Right? It will not look as simple as saying that at a given time frame, time slice, the different regions of the universe look the same. Okay, and we'll make it more specific as we go along. Okay, how we are going to use this. Okay, so the general metric is minus f1 x2 square where these as it stands can be arbitrary functions exactly. Okay, because we have not put any homogeneity and isotropic conditions so far. Okay, it's just that we have written down the most general metric in the Tx coordinate system. So the first thing we want to do is to see to what extent we can simplify the form of this metric using possible coordinate transformation. Okay. In a general coordinate transform, the metric can look complicated. Can you simplify it? Now, a coordinate transformation that we can use, as I said, we will only make use of coordinate transformations which do not touch the spatial time. Okay. In fact, that's not completely true. Okay, later on we will use the coordinate transformation involving t. But right now, let's suppose that the new time coordinate is the same as old time coordinate, so the preferred time remains preferred time. But as far as the x is concerned, it can go to some arbitrary function phi I of x prime. So we can start with this metric and make this substitution to get the new metric. Now I will not write down the details, but what we'll just do a simple counting right now. So you see that here there are three independent functions of x and t which are in this off diagonal mode of dxi dt. Okay, three independent functions of x and t. This provides three independent functions of x prime and t. Right? So what one can show is that generically, unless things are singular, by choosing this phi i's appropriately, we can get rid of these functions. In other words, you just substitute here. Then in the x prime t coordinate system, the new dx prime dt, the coefficient of that will involve f2i as well as phi I. And what one can show is that by adjusting the phi i's appropriately, we can basically make the coefficient of dxi dt prime term, dxi prime dt term 0. To adjust. Right? So generically one expects that by adjusting three independent functions, we can make any three independent functions to be 0. Okay, unless some of these functions do not appear in the transformation boundaries. Okay, which you can easily check that that's not the case. Okay, these functions do appear in the transformation boundaries, and hence by adjusting this, we should be able to make this 0. So, claim, which are not true, is that by suitably choosing phi I, you can make the new functions
So T prime.
t prime is the same as t, yes, but I have written t prime. Okay, so basically the off diagonal term, the cross term between the dx and dt can be removed by adjusting these phi's. Is this statement clear? Okay, so I'll now re-level x prime t prime by xt and drop the tildes. Okay, because after all these are arbitrary coordinates and arbitrary functions. So I'll choose the metric to be minus f1 of xt square plus f3ij xt
Sir,
Yes.
any function that we choose of t, if we take a coordinate transform,
Yes.
any function that we choose of t to transform, that only depends on t, basically means t transformed by itself. It should also be a choice of
Yes. So the point is, as I said, this is not the most general transform you could have made. You could have taken t to be a function of t prime,
So can we do that?
but not a function of t prime and x.
Yeah. I'm
Okay.
saying only t.
Only t. Yes.
Then we can make f point tilde.
No, we cannot make it yet because
This point is a function
we only
of
have a
x.
function of t. This is still a function of x and
Oh,
right. So if it was just a function of t, then you could have used that transformation. Okay, let me repeat again. So the point is, this is of course, these are the special nature of the time, right? But if you take t to be a function of t prime,
Any function of t prime will do the trick, because if I have a repetitive function like
no,
oscillator,
not any repetitive function, then it should be a monotonic function.
Yes, only then.
Then constant t prime will imply constant t, right? And the homogeneity and isotropic test requires only constant slices, right? So as long as the constant t implies constant t prime, we are satisfied.
Yes.
And that will happen by taking t to be a function of t prime. Okay. We will exploit it later. Okay, but right now, using that function, we cannot gain much because it's only a function of t, and what we are trying to remove are functions of x and t. Right? So this clearly has lot more conditions. To remove them, you have to impose lot more conditions than what you can get from a single function of t. Okay, so that's why you have not so far made use of that transformation. Okay, we have kept t untouched.
So therefore there is no option for static.
What?
Because,
No, you could in principle take this to be independent of t. Right? That will be a static element, except that that's not what you observe. Right? You can certainly construct solutions to Einstein's equations which are static. Okay, flat Minkowski space-time is like that. Right? Which is time transfer equations. Is that that's not what you observe. Okay, so you want to this metric. Okay. And now what you are going to do is to state what exactly you mean by homogeneity and what exactly you mean by isotropy. Okay, and then we will see how to implement them. So homogeneity so the statement of homogeneity is the following. Given any 2 points, space-time points, xt and yt. Okay, so same time, defined space coordinate in general. There is an isometry is isometry of the form Okay, is this statement clear? So let me explain it again. Let's suppose we have 2 arbitrary points in space at the same time slice t. Okay. Now one statement of homogeneity, which will be a somewhat trivial statement, is to claim that these shouldn't depend on x. And that will obviously be homogeneous. The metric will look the same everywhere, right? But we want to make it a little more general. Okay. So what we want to say is that given two arbitrary space-time points of this kind, we can find an isometry of this kind, okay, where time doesn't change. Isometry will act only on the space coordinate, and this isometry has a property that when it acts on the point xt, it takes you to the point yt.
So sir, that means if we go from x to y
Yes.
at a particular time, then the metric will remain same.
Yes, isometry means the function of all the metric will remain the same. It will remain this. Right? So isometry we have already defined. Right? What do you mean by isometry? Okay, isometry is general coordinate transformation that says it keeps the functional form the same. Okay. Now we are saying that that it's not just one general coordinate transformation, that one isometry, that given any 2 points x and y, we should be able to find some isometry, which isometry means that it has to preserve the form of the metric, but it also has to have a property that it takes the point x and maps it to y. That's what this statement means.
In the same coordinate system.
Pardon?
In the same coordinate system.
No, this is a precise statement. This is a coordinate transformation.
Means I'm trying to say that if you are in say Cartesian coordinate,
Yes.
in x from x point to y point will still remain in Cartesian coordinate.
Isometry means that it has to preserve form of the metric, right? And nothing else, right? Isometry means that if the original metric was dx square plus dy square plus dz square, the new metric should also be dx square plus dy square plus dz square, right? That's the meaning of isometry. But in that process, the point x gets transformed to x prime, right? And we should be able to find an isometry that takes x to y.
I'm saying that I was asking that whether this transformation corresponding to homogeneity changes the coordinate system itself.
No, isometry, yeah, it is a coordinate transformation. It's this coordinate transformation. Isometry means that when you think of this as a general coordinate transformation, it should give the same metric, right? That's how we have defined our isometry. Okay? But now we are saying that such an isometry must exist for any pair of points x and y, so that fi of x is y. Y. Yeah. Is this statement clear? In flat space, it's clear, right? What we mean by homogeneity. Flat space is homogeneous. Why? Because given 2 points x and y, you can find a transformation that preserves the form of the metric, namely just translation, and that takes x to y. Right? X goes to x plus a. If you choose a to be the difference between x and y, then it takes x to y. Right? Form of the metric remains eternal. Is the statement clear?
Sir, but if there is an isometry in the space, only in the space coordinates at a particular time slice, then
Well, isometry of course acts on the whole space time,
Yeah.
right? But the form of the isometric transformation is this, right? Which doesn't change t and changes x.
yeah, but the thing is that in terms of viewing it as a coordinate transformation,
Yes.
you're not actively changing the point view. Kind of, you're at the same point in a new coordinate system where your kind of functional form is preserved. That is
Yes.
defined as isometry. But if you change your point of view, it can in going from x to x prime as viewing it as translating in the same coordinate system between 2 points.
Yes.
Then you are in the same statement. You are implying that between at 2 points, my basically space time looks the same.
Yes. So according to isometry, like any symmetry, right, can be viewed in two different ways. One is passive viewpoint, one is active
There
viewpoint.
is probably confusion.
Exactly.
Then
But
in incorporating both viewpoints, can I not say that isometry implies homogeneity?
no, isometry doesn't imply homogeneity. Okay. simple example, take an ellipsoid. Okay, it has isometry, right? Rotation about the z-axis is isometry. Okay? It doesn't imply homogeneity because given any two points, there is not an isometry which takes you from one point to the other. Right? If it's an ellipsoid, okay, take a point. So all points on this can be taken from one to the other using isometry. But take a point here and a point here. There is no isometric transformation that takes you from here to here. Right? So ellipsoid is not homogeneous.
But the sphere is.
But the sphere is. Okay? If you have a sphere, given any two points on the sphere, there is always a rotation which takes you from one to the other. Okay? So let me repeat again. So isometry, you can think of it as two different ways. One is passive, right? You are just changing your coordinate frame. Other one is active. Okay? You take from one point to another. But this statement is independent of what viewpoint you take. Okay? This is a purely algebraic statement. Okay? This doesn't care about whether we are using the active viewpoint or passive viewpoint, right? We have defined isometry as a set of functions which satisfy certain relation. Okay? That if you make this coordinate transformation, the g prime that you get using general coordinate transformation has the same functional form as g. Okay? And now we are simply saying that given x and y, you should be able to find such an f which is an isometry and which has this property. Okay, this statement is just a statement in algebraic terms. Right? Physically, when you try to interpret what it means, the active viewpoint is more useful. That you are changing a point in space-time. Okay, but as a mathematical statement, this is completely well defined without taking any specific viewpoint.
To make sense of it physically, the active viewpoint will come to the
Exactly. So, active viewpoint is that a coordinate transformation actually changes from one point to another point, right? Not that you are using a different coordinate system, but it's a transformation that acts on the space-time.
In other sense, we just hold the manifold and move it in a different
Move
orientation.
the points, right?
Yes.
And this motion is such that the metric remains unchanged under that motion. Okay? That's the active viewpoint of isometry.
So the transformation is taking it from x to y also and keeping the metrics unchanged.
Exactly, that's right. Okay? Which, as I said, on the ellipse side, you can do if the x and y points are on this circle or on this circle. But if x is here and y is here, there is no isometry which takes you from here to here. Is it clear? So ellipsoid is an example of a space which is not homogeneous, but it has an isometry. Flat space obviously is homogeneous, right? Just translation will take you from one to the other, one point to another point. Sphere is a more non-trivial example of a homogeneous space. Surface of a sphere, right? Because you have a freedom of rotation about any axis. Okay? And using that, you can clearly show that given any two points, there is always a rotation that takes you from one point on the sphere to another point.
So, sir, this homogeneity can lead to metric which is independent of space, right?
Independent
Of space point.
Well, if the metric is independent of space, then it's homogeneous, but the reverse is not true. Homogeneity does not require that your metric should be independent of space. A sphere metric, right? Two-dimensional sphere, d theta square plus sine square theta d phi square. This is a homogeneous space, but there is no coordinate system in which the metric is independent of the space-time, right? So if the metric was independent of the space-time space coordinates, then Riemann tensor will be 0, right? For sphere, you certainly know that Riemann tensor is not 0. Right? So yes, so if the metric is independent of space, then it's homogeneous. Okay, because then the isometry is just translation. Right? If the metric is independent of space, just simple translation of coordinates is an isometry.
But looking at the problem is coming in, like if you take a sphere,
Yes.
the problem is lying behind your coordinate systems.
No, it's not on the sphere, right? Labeled by theta and phi. It's impossible to find a coordinate system if the metric doesn't depend on the coordinates.
True, but physically the two points are actually equal.
Yes, 2 points are equivalent. That's why it's homogeneous.
Ah,
Okay? But there is no metric which is independent of that point of the coordinates, right? Because then the Riemann tensor will be 0. Right? So if the metric is independent of space point, it's homogeneous, but the reverse is not true. Homogeneity does not require So the metric is independent of the space point.
So,
Yes.
if you take two different points in the space-time,
Yes.
then around the two different points, the curvature may be different, right? Gaussian curvature.
But if the metric is homogeneous,
No,
then-
if because
yeah, in general the Gaussian curvature will be different. Yes.
then how will you find a isometry?
No, then the manifold will not be homogeneous. If the Gaussian curvature is different between two different
But
points.
in space-time manifold, we at different point we will have in locally they will have different curvatures, Gaussian curvature.
So if it happens, then the manifold is not homogeneous. Right? The homogeneity says that there has to be an isometry which relates them, right? Not every manifold is homogeneous.
So space-time manifold is not
Homogeneous manifolds, no, space. There are examples of space-time manifold which is homogeneous. Right? Flat space-time is a homogeneous manifold. Right? Sphere is a homogeneous space. Okay. So you can certainly consider examples of space-time which is homogeneous, but there's a spatial. That's why homogeneity is a strong.
space cannot be like ellipsoid and
No, exactly. Right? If the space was like an ellipsoid, right, then it's not homogeneous, right? And that contradicts what you see in experiment, that the space is homogeneous at a given time size. But for this, of course, you have to separate out time coordinate, and we'll do this carefully, right, as we go along. It's not that we are claiming that a space time is homogeneous, because different times are definitely different, but the space is homogeneous at a given
Time slices are
size.
homogeneous.
Time slices are homogeneous, right? And this is the precise statement of what we mean by that. Time slices are homogeneous. Right? This is the state condition that will impose on our metric. Is this clear? So now let me give the definition of isotropy, and then I'll stop, and next time we'll try to work out what it means. So isotropy is always around a point. We're not going to define what we mean by isotropy. So given two nearby points, x1 p and x2 p at equal geodesic distance from x1 to 3. Okay, I've called it F5, so let's call it capital F5. Okay, so all the isometry is the same. X changes, but T doesn't. Such that the following two conditions hold. Okay, So let me explain. So this isotropy is always about a point, right? We fix our point x naught t. We are trying to define what we mean by having the space time to be isotropic around this point x naught. So we pick two other points x1 and x2, okay, nearby at the same time slice, and geodesics are solutions to second order differential equation, right? Geodesics is a second order differential equation. So it requires two sets of initial conditions. If you fix the initial and the final point, then the geodesic equation can be solved. Those are the boundary conditions, right? So there is a unique geodesic that connects two nearby points, and you can calculate the distance along that geodesic. Now, x1 and x2 have to be chosen in such a way that they have equal geodesic distance from the point x0. Is it clear?
Geodesic
What?
Is that we calculated
integral of
integral of ds.
Exactly. Integral of ds is the same. Okay, integral of b tau is the same.
Yeah.
Okay. Given two such points, or given three such points, the original point x0 and these two new points x1, x2, we have to find an isometry of this point, which first of all has a property that this doesn't change the point x0, and it takes x1 to x2. So you see, if we had dropped this condition, if we just impose a second one, then homogeneity will imply isotropy. Homogeneity tells us that any two points in space-time can be related by an isometry, right? Okay, so obviously x1 and x2, these are just 2 points in space-time. There is an isometry which relates them. But isotropy is more than homogeneity because of the first condition. Right? Here you are demanding two conditions simultaneously for the same function. It has to keep x0 unchanged and it has to take x1 to x2. Okay? And it's for this reason that isotropy is not a consequence of homogeneity.
So is homogeneity a consequence of isotropy?
So no, homogeneity is also not a consequence of isotropy, or not a consequence of isotropy around a point. Okay, if the space is isotropic about every point, then it's homogeneous. Okay, ellipsoid is one example, right? Ellipsoid is isotropic around its tip, right? But it's not homogeneous. So, as isotropy around every point will make it homogeneous. Okay. Also, if it's homogeneous and if it's isotropic around one point, then it's isotropic around every other point. Right? Because homogeneity means that all points are equivalent, right? You can make the metric around any point look like the metric around the other point by a coordinate transformation.
If one point makes it special by making isotropy, then every point must have the same.
Exactly. So if one point it has isotropy, then every point must have that property. Right? Even though it may not look like it has a property. A simple example again is the two-dimensional sphere. Take the two-dimensional sphere. Okay, written in theta phi coordinate system. Okay. Homogeneity is not very obvious. Right? It is homogeneous, but it's not very obvious. Neither is isotropy. Okay. But isotropy around the north pole is obvious. Right? Around the north pole, isotropy means phi goes to phi plus constant. Right? A sphere, if you are sitting at the north pole, right, then given any 2 points which are at equal geodesic distance from the north pole, okay, how do you relate them? By rotation about the z-axis. That acts, of course, very trivially on phi.
So at any point we can choose an axis and relate it around that.
Yes, that's if you know that the sphere came from the Cartesian coordinate system by writing that equation, right? But suppose somebody gave you the sphere as a metric d theta square plus sin square theta d phi square, and you didn't know what the isometric transformation is, right? Then in the theta phi coordinate system, the transformations that guarantee homogeneity and isotropy are non-trivial.
To phi plus c is the only evident isotropy.
Yeah. So the only thing that is obvious on the sphere is the isotropy around the north pole, around this point. Because here phi goes to phi. So what are the points? If 2 points are at equal geodesic distance from this, that means they have the same value of theta. Right?
Yes.
Now it's clear that phi goes to phi plus constant is an isometry on the sphere, right? Because the metric is sin square theta d phi square plus d theta square. So clearly if you translate by phi, metric doesn't change. Okay. So phi goes to phi plus constant is a trivial isometry, and any 2 points which are at equal geodesic distance from the north pole can be reached by that transformation. Phi goes to phi plus constant. That's why isotropy is manifest, right? And phi goes to phi plus constant, of course, also keeps the point north pole unchanged. Right? So in general, homogeneity and isotropy of a given manifold are not manifest always. Okay? In simple cases like flat spacetime, of course, it's manifest, okay, but not always. Okay? But this is what we will demand, right? We will not demand that our spacetime has manifest homogeneity and isotropy, but by looking at the manifold, you can see that it's homogeneous because it doesn't depend on some coordinates. That may also happen, but the general demand that we will be making on our spacetime is that it's homogeneous and isotropic in this sense, but not necessarily that this homogeneous and isotropy is visible in the form of the matrix.
Because you have assumed isotropy at all points.
Well, I have assumed homogeneity, right, and isotropy around one point, but that implies isotropy around all points. Okay. Because you know that we can test the isotropy around the point where we are in, right? Because we can look in different directions and see if they look the same. And we can test homogeneity by measuring average densities in different regions. These two imply that the universe is isotropic around every other point. Okay. So this will be our assumption. Okay. So next time what we will do is that we will try to impose these conditions on the metric that we wrote down, okay, and see how we can restrict our constants f1 and f3. f1 and f3 are arbitrary functions to begin with, right? f2 is set equal to 0 by choosing appropriate coordinate system. f1 and f3 we haven't fixed. Okay. So next time we will use these conditions for homogeneity and isotropy to fix f1 and f3. Is this okay? I think tomorrow is a holiday, so we'll have class again on Friday.